Okay, what we're going to go over today is absolute value functions and some of their transformations. First, we're going to start with the parent function, and then we're going to work through some of the different transformations of what we can actually do with some of the equations. So, the parent function would be y equals the absolute value of x. All right, so that's the parent function. What this means is these two vertical lines. What it means is any value inside the two vertical lines, whether it's negative or positive, we're going to give it a positive value. Absolute value actually means the distance something is from zero. So, if I had a basic number line with zero in the middle, and I got 1, 2, 3, and I also have -1, -2, -3, it doesn't matter whether I use a negative number or a positive number. Absolute value is the distance that number is from zero. So if I had, say, -3 as a point and 3 as a point, 3 obviously is 3 units from zero. -3 is also 3 units from zero. You can't have a negative distance. So that's why the distance from zero is always positive. That's why we say the absolute value is always positive. So let's graph this. Obviously, the easy way to graph any kind of function or equation is to do a t-chart with our x and our y values. All right, so we're going to start with nice easy input, 0. So if I plug 0 in, the output obviously is going to be 0. 0 is not really positive or negative, so nothing really changes there. We're going to use 1 and 2, some positive numbers as inputs, and we're also going to use some negative numbers as inputs, -1 and -2. All right, that way we get some numbers on the left side of the y-axis and some numbers on the right side of the y-axis. So let's plug these into our equation and see what our outputs will actually be. So if I plug -1 in, nothing changes. Y would be 1. If I plug 2 in, nothing changes. Y would actually be 2. Now, here's where the absolute value comes into effect. If I plug in a -1, even though it's a negative on the inside, these lines make that negative become a positive. So if I plug -1 in, y is going to be equal to a positive 1. Same thing for -2. If I plug a -2 in, the absolute value lines make that now a positive 2. So here's how we graph it. 0, 0 is our origin. And we got 1, 1, 2, 2, -1, 1, -2 and positive 2. And if you notice, we're a little squeaky today. It creates a distinct shape. It creates a shape that looks like a V, a capital V. That's the easiest way to remember what an absolute value function graph looks like. It looks like a V for value. All right, so that's the parent function so far. And notice that with this parent function, we don't go below 0 in this parent function. However, the lines keep going on to infinity. So if I wanted to do the domain for this, remember your domain is nothing more than all of your x values. The domain continues to go in the positive direction, continues to go in the negative direction. So the lowest domain value in the negative direction would be -infinity. And the highest x value in a positive direction would be infinity. And since those aren't actual numbers, they're more of a concept, we use parentheses around there. Now for the range, once again, my lowest number here is 0. You always put your lowest number first when you're doing interval notation. And then my highest number, well, they keep going up and up, so that would be infinity. Since we're actually including 0 as an actual data point, that gets the brackets. Since infinity is not an actual data point, that gets the parentheses. All right. Let's make a couple changes to this. Let's see what's going to happen if we make some changes. Actually, let me erase the whole thing. We'll just kind of start over with a basic graph. All right. Let me see which marker works better. Yeah, I think this one does. Sorry, dropped my towel. All right, let's add a number to the outside. And so let's see what happens here. Well, I'm going to make my same t-chart again. X and Y. I'm going to use the same numbers. 0, 1, 2, -1, -2. You will pretty much always start off with these numbers. Sometimes if the graph gets a little bit too big, you can always add a couple of extra numbers, whether they're positive or negative down at the bottom. All right, so let's see what happens here if we add a 2 on the outside, or plus anything on the outside. So if I plug in 0, 0 plus 2 is still 2 for my output. If I plug in 1, 1 plus 2 is 3. Plug in 2, 2 plus 2 is 4. So far as predicted. Now, if I plug in -1, remember the lines of the absolute value makes that -1, now a +1. So +1 plus 2 is 3. If I plug in a -2, -2 becomes a +2. +2 plus 2 is now a 4. So let's see what the graph looks like now. Let's kind of do like a rough graph here so we get the idea of what's actually happening. All right, so my Y value goes up to 4. It doesn't go below 0. And I have to go to at least 2 and -2 on my x-axis. All right, 1, 2, 3. 1, 2, 3. Put a couple at the bottom. 1, 2, 3, 4, 5, 6. All right, that's enough points. So let's see what change was made. What transition was made? 0 and 2 would be right here. 1 and 3 over to 1 up to 3. Puts a data point right there. 2 and 4. 2 and up to 4 goes right about here. Oops, I went too high. 2 and 4 goes there. Then we work the other side. -1 and 3. -2 and 4. So once again, if you notice, we still have distinct V shape because it's an absolute value function. We would still have very similar domain. The only difference here is now that our lowest number is actually at a 2. It's not at a 0. So really, what did that 2 actually do? It moved the entire parent equation up 2. So instead of being at 0 when there was nothing there, and it was just the parent function, it actually goes up 2. So anything on the outside of the absolute value functions determines where it goes on the y-axis. It can go up if it's positive. It can go down if it's negative. All right, let's do a -1. Just to kind of show you how it can actually go down. Let's do -3. So again, I'll do my 0, 1, 2, -1, -2. And we plug this in. 0 gives me a -3. If I plug in 1, I get a -2. Plug in 2, I get a -1 overall. Plug into 1, I'm still going to get a -2. If I plug in 2, I get a -1. All right, if you really notice, if I plug in a 1 or a -1, I'm always going to get negative 2 in this case. If I plug in a 2 or a negative 2, I always get negative 1. I think I just said that part. All right, so let's graph this. So now it's 0, negative 3. 1, 2, 3, 4. Put a couple on each side. 1, 2, 3. 1, 2, 3. All right, so here's my graph. My starting point is 0, negative 3. So as you can see already, from the parent function, which was just y equals absolute value of x, that would start up in the origin, it's gone down 3. And everything else should pretty much look the same. It should still look like a v. However, now it starts off at negative 3. So 1 and negative 2. 1 over to the 1, down to negative 2 is right there. 2 and negative 1, go over 2. Down 1 on the y-axis. And we go in the other direction. Negative 1, negative 2. And negative 2, negative 1. All right, so the only change here is that we've gone down 3. So anything on the outside of the absolute value bars or vertical lines will determine whether we go up or down the y-axis based on if it's a plus, it would go up like in the plus 2. If it was a minus, it would go down 3. All right, let's try something else. Let's try to put a number on the inside along with the x and see how that affects it. Remember, if I'm going too fast along here, feel free to pause the video, get caught up, take notes, rewind the video. So, all right, let's see. Let's do y equals x. Let's do plus 2. Put the plus 2 on the inside this time. Let's see how that affects it. Do our little t-chart. X and y. 0, 1, 2, negative 1, negative 2. Let's plug in our numbers. If I plug in a 0, absolute value of 2 is still just 2. Plug in a 1, absolute value of 3 is still 3. Absolute value of 4, because 2 plus 2 is 4. So forth. All right. Negative 1. Negative 1 plus 2 is a positive 1. Negative 2 plus 2 is 0. So that's a 0. So let's see what we have so far. Because I don't think we're going to actually have a V shape yet. Remember, though, we could actually add some inputs to it to try to get more of that V shape that we're looking for. So if I create my graph, and I have to go up to at least 4 on the y-axis. 1, 2, 3, 4, 5, 6, 7. That's plenty. And at least 2 in each direction on the x-axis. Let's go 4 in each direction. Because I have a feeling that we are going to go past the negative 2. All right, so let's graph this and see what happens. So 0, 2. 0, 2 is right here. And right away, you might be thinking, oh, it's on the y-axis. That must be the bottom of my V. Actually works out differently this time. 1 and 3. Go over to 1, up 1, 2, 3. Put a dot, 2 and 4. Everything's working out like it should so far. Negative 1 and 1. Uh-oh. We're continuing to go down in that direction. Negative 2 and 0. Negative 2 and 0 is right here. So far, we only have a straight line. So we got to find out, is this going to keep going down farther? Or will it hit the x-axis and come back up? So let's find out. Let's add in a negative 3 and a negative 4. See what happens. So if I plug in negative 3, negative 3 plus 2 is a negative 1. But the absolute value bars turn that into a positive 1. negative 4 and 2 is a negative 2. But that turns into a positive 2. So let's plot these points. Negative 3 and 1 would put a point right there. Negative 4 and 2 would put a point up here. Here we go. So as you can see, we still have our V shape. But now, since I've added a number on the inside, now it doesn't affect it going up and down on the y-axis. The number on the inside affects it going left or right on the x-axis. And if you notice, you might think, okay, it's plus 2. So if I had my original parent function, which look kind of like where the green is, you would think plus 2, we're going to move to the right 2 in a positive direction. But actually, the number on the inside is actually the opposite of the actual value it is. So if it's positive, it actually goes to the left. And if it's negative, it actually goes to the right. So kind of make like a little side note. It works opposite to the sign. All right, and this works for all parent functions and different functions. You're going to see this. It works this way also for the vertex form in quadratic equations as well. It's how the original equation is set up, and that's why it kind of changes that way. But it's the opposite. So that's why I moved over 2. All right, let's do one with 1 on the inside and the outside. We're not going to do a data table, but based on what we've learned so far on how the numbers on the outside affect our absolute value function, and how the numbers on the inside affect our absolute value function. We're going to do one without the data table. I know, exciting stuff, huh? So let me start to set this up. And let's do y equals the absolute value of x minus 3 plus 1. All right, so we're going to graph that without doing a t-chart based on what we've learned. Okay. So we know the parent function. Remember this? Y equals absolute value of x. The parent function had the absolute value coming up from the origin. So that's our starting point, the origin. Now, we're going to move it 3 spaces to the right. Remember, it's the opposite when it's inside. 1, 2, 3. And then this is true to form. It's plus 1, so we're going to go up 1. So 1, 2, 3 to the right, up 1. Now that is the new bottom of our V. So that equation would look like that if you graphed it. We went over to the right 3 and went up 1. The only transformation we haven't really talked about, well, one of them actually, is if you ended up with a negative sign out in front of everything, that simply just takes the V and flips it upside down, puts it on the negative side. So for example, for this one, if I made it a negative, I still would move the point, the bottom of the V, over in the same spot, over 3, up 1. But instead of going up like a normal V, it would actually go down like an upside down V because of the negative sign. Just like with our parent function, if I made that negative, everything would be the same. except the V would then be upside down because of the negative sign. It's still absolute value, even though the V is upside down. It's just that the negative makes it go upside down. That's about it. Oh, one last thing. Two more changes. If you end up with a number before the X variable, it could either make the V taller or wider, depending on whether it's a whole number or a fraction. So if I had something like y equals, and then say I had 4x, when it's greater than 1, it makes it a taller V. 1, 2, 3, 1, 2, 3, 4. Because if you think about it, it's kind of like the slope. It'll just make it a taller V. And these V's are symmetrical. So it'll make it a taller V. Not a regular V, a taller V. Because it's a whole number. And the bigger the number, the taller it gets. If it's a fraction, inside, it's going to make it a wider V. So with a fraction, and that's still positive, so we're still going to be on the positive side of the y-axis. It would be a wider V, up 1 over 4, up 1 over 4 this way. So it just makes for a wider V. All right, so that's the only other transformation. This is kind of like on the right side. It's kind of like the slope. Because notice I went up 1 over 4. And then unfortunately we have to do like the reverse slope because it's an absolute value. Same thing over here. I went up 4 over 1. It gives me a taller V. All right, so we're going to go over this in class. If you have any questions, please ask me in class. If I post this on YouTube, please make a comment below. Maybe click a little like button if I do post it on YouTube. And I will see you tomorrow in class.